Hermano and Philippe for all this week and all the scientific program plus concert on the other day where we could discover new singers. So I'm going to talk about self-similar vanishing limits, and as you will see immediately, it's very much related to what Constantin Dafermos presented on Monday. So we are looking at general nonlinear hyperbolic systems, and specifically looking at the Riemann problem, which, as you already heard, contains already a lot of information about even more general solutions of these PDEs. And we are interested here in understanding better the nonlinear waves that enter in a Riemann solution. And the new aspects, so some of this is, of course, an older question, but the new aspects I'm interested in this lecture is various problems where you have complex wave patterns. So typically the result of lax that was mentioned in one lecture will not be relevant to describe these Riemann solutions because there are other kind of waves, or the waves are somehow coupled in different ways. And so here I can specifically mention resonance phenomena, which is a situation where you have two eigenspeeds, two velocities of your system that may coincide for some values of the state and be different for other values. Phenomena of phase transitions, where you could even have complex eigenvalues that enter into the problem. And another source of complex wave patterns comes from boundary layers, where even if you have a strictly hyperbolic system, you may have somehow waves that are squeezed near the boundary that create a rather complicated pattern as well. So the main issue here, I mean, there are basically two main issues. Deriving uniform bounds for the total variation in these sort of situations. And when this can be done, try to say more about the qualitative structure of the solutions. And for instance, if you have a problem with some interface, fixed or moving, you would like to know what sort of jump condition is satisfied across this interface. So let me start with an example, which is an old example that goes back to the work of Marshall-Slemrod, which is a system of phase dynamics or elastodynamics consisting of two equations, two conservation laws. So in this part, the system is the announced as the velocity and the deformation gradient, and there is an equation of state to determine the stress as a function of the deformation gradient. So this is for the main part of the PDE, and this PDE is regularized by self-similar viscosity and capillarity coefficients, which are called T epsilon and T delta. So epsilon and delta are supposed to be small and will actually tend to 0. And so these terms appear with two derivatives of V or three derivatives of W in the first equation. And there is no regularization in the second equation because this is related, if you like, to the conservation of mass or equation of continuity. And physically, you don't expect to have any regularization for that equation. So we put Riemann data initially for that system, and we ask whether we can derive uniform bounds that will be independent of epsilon and delta for the total variation of the solutions. And if that is possible, then take the limit, end up with this first order system, and start the analysis of the interface conditions or the shock conditions that are implied by this regularization.
This power of the other P is also what?
Power of what? T.
You said the self-similar solution.
Yeah, I guess maybe this is wrong. Yeah, maybe the second one is wrong. Yeah, yeah. So the scaling is made. So this goes back, as I mentioned here, to the work of Constantin Dafermos. This scaling is a regularization that somehow mimic the physical regularization and allows you still to remain in the class of self-similar solutions. Okay, so if indeed you impose the scaling y equals y x over t, you end up with a system of ODEs with this regularization, epsilon and delta, with second order terms, second and third order terms. And now the initial conditions are sent to infinity and becomes boundary conditions for V and W in this form. So what we need to do here is to show that the total variation of V epsilon W epsilon is uniformly bounded, and then to analyze the limits whenever is possible. So I put a list here of people who have worked specifically on subsonic phase boundaries or supersonic phase boundaries in the context of this system of two conservation laws that I just wrote, which is, of course, very much related also to the Euler equations. So Shearer, Salemro, Truskinovsky, Aveyaratne, Knowles, myself, about kinetic relations for that system. Then Pfan, Salemro, Savaras, Andrianov. And there is also a list here of people who look more specifically at self-similar vanishing viscosity limits, but now for more general systems. So starting by the work of Dafermos, and then Zavaras, and myself with Zavaras on non-conservative systems. And then I wrote a couple of papers with Joseph, Rode, and more recently Bianchini with Ancona, Spignolo, Cristoforu. I've been also working on these self-similar vanishing viscosity limits. So in this lecture, what I do is concentrating on situations which are somehow not so classical, and you have this complex, or you expect to have these complex wave patterns. So more specifically, but I'm going now to move to different examples as well, but in the situation of the phase transition dynamic system, what we are able to do is to handle physical viscosity, and that implies a sort of singular behavior near the vertical axis. So if I have time, I will return to that. And we can also cover in this analysis both hyperbolic and hyperbolic elliptic regions. So for instance, this was not done in the original work of Salemrod some years ago. And the analysis also covers arbitrarily large data. Okay. Now, if I have time, I will return to that system. But before that, I would like to talk about problems that are completely related, which is first coupling techniques that we are developing these years for general nonlinear hyperbolic systems. And here you will see a connection with a lecture of Kenneth Carlson the other day. So we look at interfaces, and again, we are looking for interface conditions to be identified. And the second problem is a problem of boundary values, which I will also be talking about. So let me start with this coupling technique. So it's a joint work with Boutin and Coquel. So what we do here is that we have two nonlinear conservative and strictly hyperbolic systems, which I can write in this form. So one system is given for x negative and another system for x positive, and some of the fluxes have nothing in common at that level. And what we want to do is we want to introduce a coupling between these two systems across the interface. And the way we do that is to introduce a sort of regularization which is based on this additional variable v, which will remain between -1 and 1. And we also view the system in a non-conservative form. So this is somehow a convenient way to interpolate between the two systems. So then what I do here is I look at the Jacobian matrix of each system, so D, G minus, DF minus, and the same on the plus side. And I somehow interpolate, for instance, linearly, but it could be something more general, which presumably would give rise to different germ conditions in the end. But this is one possibility to define this matrices A0 of UV and A1 of UV. So having done that, we end up with a system which is non-conservative. So it is non-conservative. So it's given by this part of the system. So, and in addition, now we introduce a regularization both in the U variable and in the V variable. So you can see that the scaling is epsilon t for the U variable. It could be a different power, so meaning that the regularization of the interface and the regularization of, say, the shock waves that propagate outside the interface might be done in a different way depending on the choice of this exponent p. And in addition, there is a matrix B0 here, which describes the viscosity effect in the U variables. So we assume that A0 is positive definite, which is somehow a consequence of what we should have assumed on the conservative systems in the first place. And we also assume here that A0 minus 1 A1 is hyperbolic as distinct real eigenvalues. And finally, I'm assuming that one of the eigenvalues in this matrix, so one of these lambda j, I call them lambda m, I call it lambda m, could take the value 0, right? So it means that for each system, basically on each side of the interface, there is a possibility of having waves that propagate at about the 0 speed, which is precisely the situation of resonance I want to study here. So in addition to that, there is going to be a small coupling condition that says something about, say, the difference between the flux on one side and the other side. And returning to that in a minute. So the way the coupling is done here is somehow through some smallness condition, which is completely related to the usual smallness condition that you have to impose anyway if you want to solve a general strictly hyperbolic system. So, which is now what I'm doing here. So I'm stating here the result of the BV bounds for this resonance system. So saying that if you give me data, so V, I guess I didn't specify it, but V, I'm thinking that V is going from -1 on one side of the interface to +1, right? So somehow I don't want to give data for V, or I want to give this specific data if you like. But of course, you could give other data. The result of this bound will be the same. But somehow the setup assumes that you are connecting one conservative system on one side to another conservative system on the other side. So now we are assuming that the data for U are sufficiently close. And we can show that the Riemann problem admits a self-similar solution, which is a smooth solution of the regularized system, which has uniformly bounded total variation and converges to a solution of the original conservative systems, at least on each side of this interface, on each region X positive or X negative. Okay, so this result is not straightforward because even though I mentioned earlier some techniques, maybe I show that again, so that goes back, I would say, to Zavaras, who was able to treat a general class of strictly hyperbolic systems. So for this specific result, we have to use a technique I developed with Joseph here, and to cope with the fact that there is some resonance. So you have waves that may coincide, and this causes difficulties when you want to control the BV bound. So I'm not going to elaborate on the proof of that here, but I just want to mention two things related to this proof. The first thing is that because the matrix is not the identity, the matrix of diffusions that we put in the equations for U, we need to solve a generalized eigenvalue problem, which is the following. So on one side, I put minus psi identity plus A, where A is nothing but A0 minus 1 A1. And on the other side, I'm not just looking at eigenvalues of, or eigenvectors of this matrix, but I also introduce the viscosity matrix B, or more specifically, B is A0 minus 1 B0. Okay, so this is a problem which I already looked at with Joseph, that you need to solve if you want to have a good idea of what are the speeds that play a role in the problem. So if you multiply suitably by some left or right eigenvectors, you can view these relations in this form, meaning that you are introducing eigenvalues for this problem that are not quite minus psi, that are, if you like, corrections to minus psi plus lambda I. Maybe you can just look at the last line. So when B is the identity, these eigenvalues I'm talking about, this mu I of u v xi, would just be a shift of the eigenvalues of your full system in u v variables. Okay? So this would be the relevant speeds in this problem. But because we have a matrix which is not the identity, it's slightly more complicated, but yet we have eigenvalues for which we have suitable bounds that say that there is a behavior which is similar to that one, if you like. Okay, but this somehow causes difficulties, I mean technical difficulties to play with that and to indeed do the BV estimates. And the second idea which is behind this proof is that there is a need of a small coupling condition, so similar to the usual condition of small jump for the Riemann problem. And it comes in this form. It comes in the form of a left eigenvector of this matrix I just explained, times the variation in V of B times this eigenvector. So this is a condition that says that obviously if there is no V dependence, this condition will be satisfied, and otherwise you want the dependence in V to be small in that sense. So what that really means is can be clarified if you look at the P system. So let me explain the example of the P system with two different pressure laws, which I call P minus and P plus. So it means that on each side of the interface I put a P system but different constitutive equations. And even if I take B to be the identity, I still have a non-trivial small coupling condition over there. Because if you define this average matrix A by linear averaging of the gradient on each side, so gradient F plus corresponding to this flux and F minus, and if you do the calculation of this matrix, if then you compute the eigenvalues, the eigenvectors in a generalized sense I just show you, and compute this number nu, you realize this number nu is actually related to the jump of the sound speed, if you like, right? So now you're asking that the sound speeds between the two regions should be close enough, which is what I want to call a small coupling condition. Okay, so I stopped for about this issue, but there of course the next question is to analyze the qualitative behavior of the solutions, especially on the interface, because outside the interface there is nothing more to say. I mean, things are known. But on the interface, there is much more to say. But I would say the program here is not completely finished, so I don't want to enter into these details here. And instead, I would like to move on to the case of boundary conditions, where you can indeed say a lot more about interface conditions, if you like, or boundary conditions. So that's a joint work with Katie Joseph. And let me begin by explaining the setup. So a setup is a general nonlinear hyperbolic system with small data. So delta 0 measures the size of U. And we are assuming that the flux function is strictly hyperbolic, so it admits real distinct eigenvalues, lambda j, and left and right eigenvectors, Lj, Rj. We look at the Riemann problem with viscosity in the usual way. So I put on this side epsilon, u epsilon with two derivatives. And the data that we have for this equation are one data at plus infinity, which I call UL, and one data which is imposed on the vertical axis, so u epsilon of 0, which I call UB. And these data are supposed to be small, less than delta in norm. So let me just remind you that the boundary conditions were studied by a number of people, starting with Bardos, Leroux, Nedelec, myself, Ben Abdallah, myself and Dubois, Gisclancer. Again, I had some work with Joseph, and more recently Ancona, Bianchini, Cristoforo, Spignolo. They had been also looking at the boundary conditions. And one important issue here, in addition to getting a BV bound, as you see we will get, is to really understand precisely what's going on at the boundary. So what do we expect? I mean, we expect that passing to the limit, we will find a solution of this equation where at plus infinity we connect, you connect to the data, UL, which you have imposed. But what we expect at the boundary is not that the trace of this function u will coincide with a given data. There should be a layer at the boundary. So what we only expect is that this trace will belong to some larger set which you want to construct, to define from your boundary data. So you could think of it to be like a curve that passes through this point UB, or it could be a submanifold with a higher dimension. So this boundary layer set should be determined from the data UB, and the main question is how to determine this set, not to define it to be too large, otherwise you would never have uniqueness for this problem, and not defining to be too small, otherwise this data will never even be included in this set. So that's the situation. And of course this comes from the fact that you have a system which is nonlinear. It's hyperbolic, nonlinear. So the fact that it is hyperbolic tells you that you don't need to impose n conditions. I mean the number of equations, say n, this is not the number of conditions you should impose at the boundary, because only data that are somehow entering your space should be given. But since the problem is nonlinear, you somehow do not know in advance which will be, so you have a nonlinearity here. So you don't know if there is a change of sign for the eigenvalues. You don't know how many eigenvalues will be entering, or if they will be entering or outgoing. So this is a question we ask here. So to do a rigorous analysis of the boundary layer equation to analyze this set, and as you will see, there are two cases of interest, the non-characteristic case and the characteristic case. The first one being, of course, much easier. A result of this analysis is that we are going to justify this scaling 1 over epsilon. You see how it comes, even near this interface, even in the characteristic case, which is not a priori obvious that it should be the case. So let me begin with the BV bound. So we can show that if you put data, the boundary data and the other data at infinity, small, sufficiently small, then the boundary Riemann problem with viscosity admits a smooth solution U epsilon, which has uniformly bounded total variation, which is proportional to the jump of your data, and in addition converges pointwise to a weak solution of the inviscid boundary Riemann problem. That means away from the interface, everything is fine. And this function u turns out, so the limit u turns out to be a BV function connecting some boundary value, u0 plus, there's a trace of your function at the boundary, so it connects this value through various jumps and waves to the value ul at plus infinity. Okay? But so far, here, I'm not telling you anything about u of 0 plus and how it is connected. So this is the issue, that this boundary condition u epsilon of 0 equal ub is not going to be preserved as you pass to the limit. There will be a jump here, and that's something you have to study. And a last property here is that if you go far away, I mean, if y is greater than the larger speed in your problem, this function you coincide with a given data ul. So it has somehow some compact support. All the waves, because we work in a variable x over t, which plays a role of the speed. So we are actually working on a compact set. Outside the compact set, it is constant, equal to the data at plus infinity. Okay, so I'm doing now the non-characteristic case, which you will see it's easy. So it goes like that. The first thing is to extract a boundary layer equation, as was done under different assumptions by Denisser some years ago. So what we prove here is that there exists some value v infinity, and there exists a smooth function v of y, which satisfies this first order ODE, so describing somehow the interior layer of your solution near the boundary. And this function v of y at 0 connect ub, right? And at plus infinity, take some value, I call v infinity, which of course I would hope that this layer go from the data, UB, to the trace of the solution. Okay, so that would be the best situation. But this is not what I get here. What I get for the moment is only that I get a layer function which goes from the given boundary data to some limit at plus infinity, I call V infinity, which only satisfies this condition, that the fluxes coincide. Okay, so it's a weaker condition. Yeah.
But since you are in the non-characteristic case,
Yeah, it's the next line, Denis.
it's invertible in your small ball.
This is the next line, Denis. So just give me time to to explain it, right? I know you are the expert here. Okay, so the next line here, I mean, this next paragraph is telling what Denis wanted to say, is that if you assume that 0 is avoided by your solution, you are in the non-characteristic case, okay, then I want to define this set, this boundary set, right? This is what I want to do. So I put it here. E of UB, how I'm going to define it. So I decide that this set will be the set of all admissible boundary values, V infinity, which I found by solving, which I can find by solving this ODE. So you start from the given UB, solve this ODE, whatever V infinity you will get, you put it in this set. Okay? And you call that your admissible boundary set. And so the claim now, I mean, the observation now is that F is locally 1-to-1. So of course, this identity on the flux is equivalent to an identity equality on U, and therefore the limit that you obtain satisfies the boundary condition in the way I formulate it, and and that's the end of the story. Except that you have to check that this set is not too large somehow, right? So you need to show uniqueness. So this description here only tells you about the existence of a solution satisfying this formulation of the boundary condition. And now to show that this is completely satisfactory, you make some more observations that the first line is I just repeat what I told you, that given UB, UI, there exists a BV solution to the Riemann problem satisfying this condition the way I just defined it. And the second part here is to describe something more about this set. So I'm assuming now that each characteristic field is genuinely nonlinear, and we can show, first of all, we can show a uniqueness result that the Riemann solution is unique in the class of piecewise smooth self-similar solutions. So meaning that your boundary set is fine, it's not too large somehow. And we can also check the local structure of this set, which is also something we expect, that this set contains a given point, UB, and locally near this given data, it is a manifold, and the dimension of the manifold is related to the number of eigenvalues, which positive or negative sign. Okay? So, in addition, in the interior, the Riemann solution satisfies the Lax or Liu entropy condition. And of course, in the special case where you would take a data which belongs to that set, the Riemann solution would just be a trivial solution. Okay, so that's the end of the story for the non-characteristic case, which is, as you see, easy to handle. And now we move on to discuss the characteristic case. So I'm now assuming that there is a P, lambda P, some index P, such that 0 might be taken by your solution. And I also normalize the boundary data to be entering. By that I mean that lambda P of UB should be taken to be positive, or I could say positive or 0, right? So somehow you can always do this normalization. And what do we need to do? So again, we need to introduce a definition of the set of admissible traces, and the one I gave will not be suitable here. And I want to mention some earlier work here on scalar conservation laws that I had done in part with Joseph, that we observe that the set of all limits V infinity that you could get, so in the scalar case this is very easy to check, is not closed. So this set is not closed. And another observation is that if you look specifically at a convex flux and you take the closure of that set, you see that so this will add 1 point. So there is 1 point. If you have an interval, and this interval is somehow at an open end, but if you add this point, you see that this point cannot be described by a boundary layer solution. Okay? So I just mean that there is really things that you can do completely explicitly in the scalar case, and you somehow understand what should be done in a scalar case, and what I'm actually discussing now is a system situation. Okay, so first of all, this equation is not going to determine U0 plus uniquely because it's not invertible. And then you could say there is an easy fix of this set, right? So you could decide, okay, it doesn't matter. I'm going to put in my admissible set all the points I was already able to achieve by solving this boundary layer equation, but then I will also take everything else which is solution of that equation, okay? But, so of course, trivially, you would get the condition that you want. But this is certainly not satisfactory. I mean, you can check in the scalar case, for instance, this is not satisfactory because it would not give you uniqueness. So you have to do something more clever. And this is a place where really we return to the BV analysis and the way the solutions were described in terms of expansion along wave strengths, etc. So here I realized that I skipped some parts, so I did not define what I really mean by this function gk, phi k, etc. So let me see if I can still explain something without that. So this function phi, they play the role of the derivative, of the normalized derivative of the solution. So you should think of the phi k to be an approximation of the k component along the eigenvectors of the derivative of your solution. So take your solution, differentiate it, and make a decomposition of that on some basis of eigenvectors that depends on your solution, and then take these coefficients ak and approximate them by essentially these functions phi k. Okay, so there is some normalization, some strengths, etc. But it's basically this meaning, and the function gk. So if I have time, I can show you that in more details in the next section. And the function gk, they basically serve to define this function phi k. Okay. So, I know this is not very explicit, but maybe that's enough to understand the story here. Okay, and so what is important now to see is that now you want to say something about this trace, right? So this is a game. The game is to say something more than you have not seen before. And so the observation now is that this trace is outgoing. Okay? Or coincide with the boundary data UB. So I think intuitively it's quite clear that if the waves, say, locally are entering for that family P, the boundary data you expect it to be achieved, to be taken by your solution. Otherwise, you are in a situation where you are in the outgoing case. Okay? And so this is what I'm explaining here, I'm proving here, saying that if the function phi have a support which contain the zero value, x or x over t equals 0, then we are indeed in this situation that lambda p of u of 0 plus is negative. If we are not in that situation, there we are in a case where there is nothing interesting somehow going on near the boundary, and you can expand your solution in the form u of 0 plus plus ub, where the next term in this sort of expansion here is going to involve only indices j that are less than p. And when p is 1, there is a stronger property, but this is maybe not so important. But the main point is this result here, which I just want to emphasize that it really uses the BV analysis and the expansion which is behind this BV analysis. Okay, now there is an additional piece of information that comes from from that. So if we take an asymptotic value V infinity, which has this positive sign, then we can expand it also in a similar form as the form I just explained for the trace in the second case. Okay? So you can show that V infinity is equal to UB plus some other component. Right? So intuitively, it means, roughly speaking, that V infinity and UB coincide up to some garbage. And now I get to some of the final point, is that if you assume that the P characteristic field is genuinely nonlinear, you can show that if you pick a state U star which has 0 value lambda P, then you can show that in sufficiently small neighborhood of that, the fact that f of u is equal to f0 would imply that u equal to u0. Okay? So you have some sort of invertibility condition modulo the assumption that you already have an information about the sign of lambda p. Okay? And you have the same conclusion on the other side if the two states you are looking at have a negative value of lambda p. And this observation related with the previous things allow you to conclude and to obtain this result. So the first thing is to return to the definition of the admissible set, which now we define like so. So we define that the set is a set of all V infinities that we already were able to reach before by a boundary layer equation, and we add to it not all solution of that equation here. So this is an equation where V infinity is any asymptotic value of the boundary layer equation, and V infinity tilde is anything that satisfies this equality for the flux, plus in addition the fact that lambda p of V infinity should be positive. Okay? So roughly speaking, we are only taking half of the solutions of that equation. And the result now is the following, that if we are in a characteristic situation with normalized boundary data and the P characteristic field is genuinely nonlinear, then we can show that the Riemann problem admits an entropy solution with bounded total variation, which satisfies this new boundary condition here. So somehow this is the optimal result that you would expect if you compare to the scalar case. Things work nicely. I mean, the typical picture for the scalar case is when you have a convex flux and you impose a data which I call UB, which is positive, right? So this would be the case where the flux is equal to U squared. And if you compute this set of admissible boundary data, what you find is that your solution can either take exactly the values that you want to impose, or otherwise it has to take values that are in this interval here. Okay? So either the solution has taken exactly what you wanted, or otherwise it's somehow very negative, and this point is precisely determined by the condition that the flux at this point, say U star, is f of UB, and there is a condition on the sign also that this sign was positive here, f prime of UB was positive, and you have this condition here that f prime of UB is negative. So you can really check from the scalar case that everything is as we expected. And for instance, the value minus UB, so it means this value here, okay, it belongs to the new set, but it was not in the older set. Okay, you could not, as I said before, you could not reach this value by a boundary layer equation. And I mentioned that before also, that this scaling 1 over epsilon is the scaling we used to derive this boundary layer equation, and it is justified in a case of a characteristic boundary, but it's connected with the fact that we assume nonlinearity. So for a nonlinear characteristic boundary, it is justified, and presumably a different scaling would be necessary if you really would like to describe also this point by a boundary layer equation, which I'm not doing here. Okay. So it seems I have time to also discuss the last case here, so the last situation, where now it's a somehow different story, is that even the BV bounds are going to be complicated to obtain, right? So in previous case, main analysis was about boundary interface, boundary conditions, but now even deriving BV bounds is going to be tricky. So I'm discussing here the elastodynamic system I had in the beginning, so it might be good to show it again. So let me do that, return to the beginning. So I just would like to show you the system we are talking about now. So I'm returning to this system here, two equations, vanishing viscosity, capillarity, and I want to tell you about BV bounds for that. And as you will see, the assumptions, the results, there are actually 4 different results we can state, depending whether this sigma here, this sigma is increasing or not, so hyperbolic case or hyperbolic elliptic case, and whether you put this delta to be 0 or non-zero. Okay, so this gives you 4 cases, and in the 4 cases you get, as you go along, the system becomes more and more complex, and you get weaker and weaker result, but somehow in each step the result seems to be the optimal one, at least with the technique of BV bounds that we use. Okay, so I guess I have only a few minutes, so I will not go into the proof, but just show you probably 4 statements. Okay, so the first statement I want to show is a case where you assume that the system is hyperbolic, strictly hyperbolic. So I put this assumption on sigma prime bounded below. And the result is that for any Riemann data, VL, WL, VR, WR, the viscous Riemann problem without capillarity for the moment admits a solution V epsilon, W epsilon, which has uniformly bounded total variation. Therefore, you can take the limit and show that there is, in the limit, a weak solution of the inviscid Riemann problem. Okay, so that's the result that we were hoping for. It's not completely standard because if you look carefully at the proof, which I will not show, you can see that W epsilon, V epsilon, although they are smooth, they are not C infinity. They actually contain a mild singularity on the 0 axis. In the following sense that the derivatives up to some very high order, C over epsilon, are continuous, but not if you go beyond that. But somehow it does not really matter, because if you take epsilon and go to 0, this will go to infinity, and somehow you can get a solution as smooth as you want as epsilon is going to 0. So, meaning that near the interface, really nothing is going on, but still there is some hint here that it might be more complicated if you relax some of these assumptions, which we now will do. So what I do now is I keep the strict hyperbolicity, but I add the capillarity. So adding the capillarity is a little bit dangerous because it introduces oscillations. The first term in epsilon regularizes the shocks, but the terms with the delta introduce oscillations. So the result here is that for any data, the regularized Riemann problem with viscosity epsilon and capillarity delta, which we take in this form, so this is some of the scaling of interest in this problem. So this regularized Riemann problem admits a smooth solution which has uniformly bounded total variation, and again converges pointwise to a weak solution. So it seems to be again quite nice, but the proof is really of a different order of difficulty because it was second order before. Now we are talking about third order equations. So the proof is really different from the one before. But yet, things are not so bad, and this should encourage us to relax still more the assumptions, and this is what I'm doing here, where now I'm assuming the strict hyperbolicity only for large W. Okay? So now you have to think of a sigma which has an increasing region, and in this decreasing region, and in that region the system is only elliptic. right? So you make a regularization of a system which is hyperbolic for large W, elliptic for small w, and there is a condition of how sigma will grow for w, which is not very important. And we have this result that if we pick up Riemann data in this region of strict hyperbolicity, somehow outside this elliptic region, we can prove that the viscous Riemann problem without capillarity for the moment admits a solution V epsilon W epsilon, which has uniformly bounded total variation. But here there is a new feature in these solutions, in the sense that you can only control the total variation away from y equals 0. And more precisely, I have a control of the total variation with respect to the data here, but this total variation, which since it is smooth, it's just the L1 norm of the derivative, but there is a weight here. Okay, there is a y that comes here, which means that I have actually no control of this guy very close to y equals 0. And therefore, we can only conclude that the conversion pointwise happens away from this interface, and we do expect a shock layer to develop at y equals 0. And if, for instance, you look numerically, you do see oscillations on this vertical axis, and so that seems to be, I mean, something you expect, but yet we'd be happy to tell more about that, which is not yet the case. But still, we have this BV bound, which works quite nicely. And let me conclude with most general situation, where now I introduce the capillarity. So I assume that the capillarity again is of the form gamma epsilon squared. Gamma is fixed, epsilon is going to 0. And I'm assuming that the strict hyperbolicity is satisfied for large W, and some growth condition for sigma at infinity, plus this condition here, which I'm going to return in a second. But so assuming this condition, the result that we get here, so remember that we have an equation with viscosity, which is nice and regularize the shocks, but also we put capillarity, which introduce oscillations, right? So there are wild oscillations in your solution when you reduce the parameter epsilon. And in addition to that, we have a system which is not even hyperbolic. It has a region where it's completely elliptic, right? So it's really a mess, and yet we can get some result, which is this one, that we can show that there exists a solution V epsilon W epsilon, at least outside some region. So you should think of Y0 to be small. Why? Because if you return to that, Y0 has to be greater than this quantity here. C is a constant, and only gamma is really relevant. And gamma is somehow the amount of capillarity that you allow yourself in your solution. So you should think of gamma to be fixed but small, meaning that Y0 will be small. And therefore, you control the solution everywhere except in a narrow region defined by y less than y0. And so outside that region, you have a uniform total variation bound, like before. And you have a conversion pointwise outside this region to a limit, which is a BV solution of the Riemann problem. So you have a situation where you can show the existence of your solution outside some interval with BV bound. And there is a small, narrow region defined by this interval in which you expect to have a highly oscillating pattern, probably not strongly converging. So BV bound certainly would not hold. And the thickness of this is determined by the relative amount of dispersion that you allow yourself in this approximation. These oscillations are observed numerically, and they are not expected to be treatable by these BV techniques. Okay, I should stop here. Thank you.
Thank you. Any questions, comments?